Okay, welcome to Tuesday, November 24. Remember, this is our only meeting this week. You have Wednesday, Thursday, and Friday off for the Thanksgiving holiday. So enjoy your slight break right there. Now let's look at our website just quickly to show you how that impacts what we're doing. Let's get over to Math 119 homepage. Just the giant scheme of things. You see you've gone through 12 full weeks, and we just have a couple weeks left. And today we're going to look at drawing quadratic functions using our knowledge of solving quadratic equations. These two sections today. And we have no meeting on Thursday for Thanksgiving, no office hours on Wednesday or Thursday or class sessions on Thursday. And then we have 2 quick weeks to finish our work. And the last week we'll take our exam. And it should be similar to the first exam. You know, we're going to review one day, and then you'll be working on the exam in the next day. I don't want to give that up. Let me go back to that screen for a second. Just remember this. Under our homework, you ordinarily hand in problems every Wednesday. That's our schedule, right? But this Wednesday, being the holiday break, I did not set any homework to be handed in on this Wednesday. So right now you're working on homework 10, but you're going to submit it next Wednesday. And the same with these sections from the XYZ homework. Now, we've covered sections 8.1 through 8.4, so maybe you've been already working on these. You should be already working on those so that you don't have crunch time and do 6 sections just before that December 2nd deadline. So keep working on the XYZ sections, get them completed, but you don't have any XYZ homework or written homework due tomorrow. You have a homework that I still am reading right now, and I'll probably have that posted and graded later today, and more likely tomorrow. And I'll send out emails when I do that. I wanted to show you a couple things I've added to this week. I have actually quite a few videos about completing the square and the quadratic formula. Just very short, sometimes 1 or 2 minute videos about practicing completing the square of the quadratic formula. And I added those to our topics list. So you may find these useful. I would think you would find these definitely useful. And you want to be proficient at completing the square and the quadratic formula. We'll use those both today in the graphing. But if you just want to see examples done, short examples, and some quick explanations, check out some of these additional videos I added. I've already given you handouts about the quadratic functions, completing the square examples, completing the square and the quadratic formula, but I want to highlight 2 additional handouts today. Parabola facts and drawing parabolas. So today our mission is to draw parabolas. And I want to give you just a shape of a general parabola and the key points on a parabola. So this is a summary of the things we're going to use to draw parabolas. These are parabola facts. And you could present the parabola in the form ax squared plus, whoops, it doesn't help for me to enlarge it on my side. Let me circle this. You could present the formula in what people call the standard form, which is ax squared plus bx plus c, in which case you identify a vertex quickly, and then you pick points on either side of the vertex to draw it. Or, let me clear that so I can advance the paper. You can set up the parabola in what's called the vertex form, where you highlight the vertex position H and K and use that to set the vertex and choose points on either side of the parabola. I mean, we invested quite some time in drawing lines, and lines had some very particular things, slope, intercept, that made them pretty easy to draw, a pattern that repeated and repeated. Likewise, parabolas have a key pattern that repeats and repeats. And they're, not as simple as lines, but they have a lot of symmetry, as you can see from these drawings. So this handout called Parabola Facts would be useful to you. I also have a fancier handout about drawing parabolas. And I'm not going to present things exactly this way, but if you want to get deeper into drawing parabolas, you can look at this handout called Drawing Parabolas. And it looks hand-drawn like this. And it focuses more on the symmetry and the shape of a parabola, this beautiful curved symmetry of a parabola. And that might help you dig deeper into drawing them, but I'm not suggesting that you must draw parabolas as I'm showing on this sheets. I'm just giving this to you as extra practice. Okay, let's back out of here. So those are 2 handouts and a lot of videos that can help you as you're working this week. I also had videos about the arithmetic of complex numbers that I added here that you might find useful also. Okay, so that's the plan for today. Let's give it a go. And then you can get off to your extended weekend. So we've been examining for a couple days now quadratic equations. And we even have a method of always solving these, a method that always works called the quadratic formula. I'm running some vocabulary by you here, just so that you have your terms straight. This was called the quadratic formula. Now, neither an equation nor a formula, but related to both, is what you call a quadratic function. What if you just focused on not when this is equal to 0, but you rather focus on what kind of values you get out when you put in different x's to this equation, to this expression. So this is called a quadratic function. This is not super critical for a test or anything. I'm going to quiz you on what some vocabulary means, but I do want you to keep this straight. This is the quadratic equation, this is a quadratic formula, this is a quadratic function. Even though the names are kind of close together, they do mean 3 separate things. You want to keep that straight.
Professor, you're still screen sharing.
Oh, go ahead. Okay, got it. Thank you. Okay, let me do 2 things. I have to increase the speaker so I hear you. So thank you for jumping in. But I also have to come back here and pin this paper. Okay, better. Sorry about that. Fix this here too. So everybody's connected, everybody's recording, and we got that going. Good. Okay, so just to say that once again, if you didn't have that screen in front of you. This is called the quadratic equation. This is called the quadratic formula. This is what we're focusing on today, drawing quadratic functions. The terms are really similar, but don't mix them. quadratic functions are commonly called parabolas. That's their technical mathematical shape name. Now, the way we're going to draw these is a mixture of key points and transformations. So that is our only mission today. But I want to show you how to draw these as quickly as possible. And the quickest way to draw these, quickly and accurately, of course, quickest and most accurate way to draw these is to use transformations and key points to kind of like anchor the beautiful symmetric parabola shape. I want to write this down in case anybody's reading these notes scanned later. Our next homework. Written and XYZ is due on December 2nd, not tomorrow night. See our website. Okay, so let's launch into graphing some parabolas from the simplest, most direct to more and more complicated ones. So here's 3 simple parabolas. Say y equals x squared, y equals 2x squared, y equals minus 1/2 x squared. And do not say, because they're simple, they're not worth looking at, or they're too easy, I could do that too quickly. There's something I want you to learn in particular about these 3 examples, even though they're kind of like very short examples of quadratic functions. Okay, no bx. There's no piece that's just an x. There's no constant on the end. So this is a really abbreviated parabola. Just x squared and a number in front of the x squared. And notice that all 3 do have numbers in front of the x squared. The minus 1/2 in front of the x squared, the 2 in front of the x squared, that's obvious. But even here, there is a number in front of that x squared. Don't forget that. The number is 1. So here, the a is 1. Here, the a is 2. And here, the a is minus 1/2. Don't forget that, because that's going to be important in the drawing. Okay. I set up now just a simple table where I show you y and x squared, x and x squared, x and x squared, and then 2x squared. I don't have to make too complicated of a table, but this time I want to show you both x squared and 2x squared side by side. And then likewise for x squared and minus 1/2 x squared. If I show you these tables once, then the pattern that's contained inside them, you will take to every parabola, no matter how complicated. So I'm not going to draw lots of tables when I want to graph these, just this one time, so that you can see a famous set of points. So when I'm graphing parabolas, the first thing I do is basically focus on the easiest points I can insert. For squaring things, the easiest thing to square is 0. The square of 0 is 0. 1 is easy to square. 1 squared is 1. Excuse me. And 2 squared is 4, 3 squared is 9. Those are pretty easy points to square. Also, squaring negative numbers is not a bad deal, because negative number times a negative number is positive anyway. So negative 1 squared is also 1. Negative 2 squared is 4. and negative 3 squared is 9. So here's the first cool pattern you see, that as you add 1 or subtract 1 to the number you insert, in a line, the y values would move in a constant fashion too. They would move a 3 or a 5 or a negative 2. But the parabola pattern is very different. The first time you move away from, and I'm going to call this 0, 0 the center, or the fancy word is the vertex, the center of the parabola. The first time you take a step left, -1, or right, +1, notice you add 1 in both directions. The next time you take a step either to the left or to the right, notice you added 3. And the next time you take a step to the left or right, notice you added 5. Now don't fall into this trap. Oh, this is a simple parabola. All the parabolas are going to be different after this. Well, be patient. Look at this pattern, this 1, 3, 5 pattern. It allows you to predict every next number you need. For example, if you took a step 1 farther to +4, I bet you +1, +3, +5, I bet you the next step here would be +7. And it is indeed +7. 9 plus 7 is 16. 16 is 4 squared. And that +7 would also apply up here, because -4 squared is also 16. 9 plus 7. Now, right now, this looks like too much information. Where am I going to put all these points? Hang on for a second, because we will draw a really nice parabola with this. But first, I want to burn this pattern in your mind. Now let's look at y equals 2x squared. Just from the table of x and x squared, I can set up the exact same points: 0, 0, -1, 1, 1, 1, -2, 4, 2, 4, 3, 9, 4, 16, if I wanted to, if I had that much space. But what does the 2 do? The 2 doubles each of these numbers. And that's not hard to calculate. Double 0 is 0. Double 1 is 2. Double 1 here is 2. So I could fill in this column as fast as I filled in the column before. Double 4 is 8. Double 9 is 18. Double 10 is, double 16 is 32. And the same here, double 4 is 8, double 9 is 18, double 16 is 32. And your first reaction is, well, the 1, 3, 5, 7 went out the window. But write down what you did do. Do you see that this is +2 times 1 when you moved up 2? Do you see that this is plus, from 2 to 8, is +2 times 3? From 8 to 18 is +2 times 5? So do you have the, what is it from 18 to 32? +2 times 7, 14 more. Do you see you don't have the 1, 3, 5 pattern? No, you do, except it's 2 times 1, 2 times 3, 2 times 5, 2 times 7. And likewise in this direction. So what I'm showing you about parabola in these tables, we're going to do tables maybe once or twice and then never again, because this pattern is going to be burned into your eyeballs. What I'm showing you is this 1, 3, 5, 7, 9, 11, this pattern of adding ever increasing odd numbers works for this parabola And it works for this parabola, except here I'm being modified by 2. 2 times 1, 2 times 3, 2 times 5, 2 times 7. That means 2, 6, 10, 14. Now you know what you're going to see in this last table. If I plug in 0, 0, minus 1, 1, minus 2, 2 4, minus 3, 9, minus 4, 16. I didn't space myself very nicely there. Plus 1 and 1, 2, 4, 3, 9, 4, 16. What happens if I multiply each of these by minus 1/2? Okay, I'm going to create fractions. I don't enjoy that. But minus 1/2 times 0 is still 0. Minus 1/2 times 1 is minus 1/2. Minus 1/2 times 4 is minus 2. Minus 1/2 times 9 is minus 9/2. Minus 1/2 times 16 is minus 8. They're not all fractions. Minus 1/2, minus 2, minus 9/2, and minus 8. Here, do you see all the points have negative sign in front of them? When I graph them, they're going to be opening downwards. But do you see the 1, 3, 5 pattern? This is minus 1/2 times 1. From minus half to negative 2 is minus 1/2 times 3. From negative 2, which is negative 4/2, to negative 9/2 is negative 5/2. That's minus 1/2 times 5. And from negative 9/2 to negative 16/2 is minus 7/2. That's minus 1/2 times 7. You still have the 1, 3, 5 pattern, but it's been multiplied this time times the a in this problem, which is minus 1/2. Now, no matter how complicated a parabola gets, it always obeys this pattern. Of course, if the a is a fraction, this pattern is kind of annoying to calculate right down. So I crunched those in there way too tight. Now let's draw these and show you how fast the drawing becomes with these numbers. I'm going to draw these side by side here. I'm going to get some space going on. I don't think I can really make your windows that much larger, but I'll move away from these tables when I need to. Let's just draw the graph. So in this first case, I'm going to mark 0, 0. And then 1, 1, and minus 1, 1. Do you notice I took one step left, one step right, and I moved up 1. Next time I take one step left and I move up 3 to 4. 2, 4, minus 2, 4. I haven't added any scale yet. I'm about to add scale. Next time I move over 1 and I move up 5 to 9. Okay, I think what I did is didn't leave myself a heck of a lot of room at the top of the paper. I cannot go 1, 3, 5, 7 up would be 16. I haven't left myself a lot of space for that. Let's put in some scale so that there's no misunderstanding about the points I'm using. You always have to mark and label scale in your graphs. And you always make sure your scale is consistent. That means the same number of boxes means the same number of steps in the whole axis. You can have different scales on the horizontal and vertical axis, but once you pick a scale on an axis, you have to make every box worth the same amount.
I have a question.
Go ahead.
So let's say we're drawing multiple lines and there isn't enough room to actually write out the numbers on the actual graph itself. Is there another way to write it competently?
Are you talking about making this table or making this picture?
No, like, do you see on your graph how you wrote like 2, 4, 2, -4. Is there another way to write that so where you don't have to have the numbers on the actual lines itself?
No, and I would say you got to put numbers somewhere so people are not like in the dark. Now you could say, "Oh, you did too much writing." Okay, I'll take out that 2. And you still understand me now that every box is worth 1 step. So you could argue, not argue, you could debate, do I have to put lots of numbers down? No, really, you just need a number to show someone what the scale is. The moment I cover up that 2 with my finger, you look at the 4 and you still say every box is worth 1. But you got to have some reference so that people don't get lost. Same thing here. I could have said 2, 4, 6, 8. I could have said just 4 and 8. But some kind of reference. I gotta make sure I'm not completely sure I'm following your question yet, but wait for the next graph because I think I'll show you a different scale there and that might help you see this. Now, what I'm gonna do now that I have these points is I'm just gonna smoothly, gently round it at the bottom and flat, draw a parabola, no pointy V shapes. These are smooth, gentle curves. If you want to see it that way, you can draw this on your calculator Desmos. There's no pointy V shape at the bottom. That bottom is smooth, gently rounded, and flat at the very bottom. This is a good graph of y equals x squared. Now let me graph y equals 2x squared and show you a nice little trick. Well, I've got all the points. They're going to be starting at 0, 0. But before I start launching this thing, I look at the points that I'm going to draw. 2, 8, 18, 32. No, no, no. I don't have space for that. You know what I'm going to do is, how about I'll keep the scale the same here. Every box is worth 1 step. But because in this problem, the A was 2, what if I pull this trick and say, I'll make every box worth 2 steps here. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Now, I don't want to write 2, 4, 6, 8. I don't want to clutter this. So if you don't want me to clutter too much, at least let me say 4, 8, 12, 16. And maybe you even consider that cluttered. That's okay. Everybody's got a different taste. But you got to give me something to see the scale, both horizontally and vertically. Here I was pretty spare on the x-axis. But now let's put in the dots. And I want you to see something. 1 and 2 is right there. Minus 1 and 2 is right there. 2 and 4, sorry, 2 and 8, sorry, 2 here and 8 here gives me this point. If I take another step up, I go up 2, up 6. Now I go up 10 from 8 to 18, which is the next box past 16, since every box is worth 2. Now look at this parabola. And you say, that's the same parabola you just drew a second ago. But I say, no, it isn't, because I've got a different scale. The shape is the same, but the scale was different. I did not have any intention of counting to 32 boxes. I would have run out of paper, even if I'd used my whole piece of paper. But since the A was 2, I said, okay, maybe I could scrunch this person down by counting by twos on the x-axis. So here's a really important trick. You, I want to be kind of provocative, are the scale master. That means you can choose a different scale on the axes if it helps you fit in the points better. Now, if I had tried to draw that graph here on top of this graph with this scale, notice what points I would get: 0, 0, 1, 2, minus 1, 2, and then 2, 8, and I would be already off the charts. So I acknowledge that this second graph is taller and faster growing. But if I just want to show you this shape accurately, I can show you by drawing a thin parabola on this scale, or I can show you by drawing a gently rounded parabola on this scale. Okay, one more lesson, and then we can launch into fancier parabolas. So let's take this parabola right here. Make some space on my desk, and I'll move to the side. Now this parabola is the first parabola I'm going to draw that's upside down. And I know it's upside down because the a is negative number. But now let's look at these points. I need to mark half points. Now, there's a couple different ways I can mark half points. And so I could show you in two drawings here, but first let's get everybody centered. So here's an x-axis, and all the action in this parabola is going to be below the x-axis. So I make sure and leave myself plenty of space down here. Now I can still draw the points from -4 to 4. I can still mark the scale on the x-axis as I did previously. But notice on the y-axis, I am counting often by halves. 1/2, even -2 is 4 halves. 9 halves. So let's mark these carefully. I got the anchor point 0, 0, which is still my vertex. But when I went to 1 and -1, I only went down 1/2 step. So if this is a -2 and this is a -1, then 1/2 step is cutting the box in half. I can eyeball half a box pretty well. So I don't mind drawing that point at the half box mark. That's the 1, 1/2 negative, and -1, 1/2 negative. Let's draw the 2 and -2. Okay, that's pretty easy one to draw too. Let's draw the 3 and -4.5. You add more scale if you like here, right? -4, -5, -6. Where's -4.5? There's a -5. So there's -4.5 at 3 and -4.5. And at -3 and -4.5. Do you see the symmetry? Every time you draw one dot for a parabola, you automatically get a second dot for free on the other side. How about 4 and 16 turns into -8? -8 would be down here. You see that gentle parabola curve going through those points. The only difference is this time it's upside down. Now I got no action up here on top of the x-axis, so I don't have to draw lots of marks up here, but I'll just fill in some marks. Now this is just about a perfect drawing. Axes marked and labeled with scale, y-axis marked and labeled with scale, x-axis named, y-axis named. Dots are predominant, are demonstrated very clearly. Then I just go smooth and round through one point, head to the next, through one point, head to the next. and you make this beautiful, gentle parabolic curve.
So there's no point at the vertex of the parabola?
Oh, there is. It's called the point 0, 0.
No, I meant like the actual shape, like it's completely curved. It's not like more of a point. It's just completely curved.
If I did a super zoom on it, it would look pretty darn flat. So what do we want to call this vertex? It's a turning point. It's where the thing turns from going up to going down, or in the other ones, from going down to going up. So there is a point there. It's just kind of the bottom of the bowl or the top of the mountain, depending on which way your parabola is opening. But the key facts we learned here is if a is a greater than 0 number in our ax squared, then this parabola must open up. And if a is less than 0, this parabola must open down. And the a even counts the steps. I went down 1/2. Then I went down 3/2. Then I went down 5/2. That 1, 3, 5 pattern to get to -8 from -4.5. I went down 7/2. Keep that 1, 3, 5 pattern in your mind. It's not the only way you can draw a parabola, but it's excellent for drawing some basic parabolas. Now this truth right here works out even when I have an x term or a c term. Positive a always means opens upwards. Negative a always means opens downwards. I got to show you what these other pieces do though. Okay, let's try again. What if I now graphed this parabola? Now the parabola x minus 3 squared, since you know how to FOIL stuff out, you know that you properly should FOIL this out to x squared minus 6x plus 9. But let me just keep the x minus 3 in front of you for a second. Let's draw these two parabolas. And now I'm going to get to the place where I am not going to draw a table this time. I'm just going to use the pattern. What's the pattern for x squared? Over 1, up 1, over 1, up 1, over 1, up 3 more, over 1, up 3 more, over 1, up 5 more, over 1, up 5 more. This is height 9, height 4, height 1, height 0. 1 step, 2 steps, 3 steps, 4 steps. I don't need to have that much detail there. 1 step, 2 steps, 3 steps, 4 steps. When you write every number, you might think you're writing nice and completely, and I don't mind if you do, but it is a lot of writing, and sometimes it gets crowded. Okay, draw the parabola. Make it smooth and symmetrical. Sketch over it a couple times to make it appear nice and smooth. What is the difference between y equals x squared and y equals x minus 3 squared? The difference is the center. This is centered at 0, 0. Well, centered, or the fancy word, is vertex. But if I put a 0 in here, I get 9. Why do I get 9 if I put a 0 in there? Because negative 3 squared, 0 minus 3 is negative 3. Negative 3 squared is 9. Where did my vertex go? Well, think about it. How am I going to get a 0 coming out of here? If I want x minus 3 squared to be equal to 0, I'm going to have to stick a 3 in there. So notice if I put 3 in for that x, I get 0 output. Now let's try my 1, 3, 5 pattern. If I go left and right one step, I go up one step. If I go left and right another step, I go up 3 steps. Notice if I go left and right another step, I go up 5 steps. 1, 2, 3, 4, 5. Bingo, I hit that point. And it's symmetric partner on the other side. So let me put some scale in here. Not at every single mark, but every other mark I put a scale. I'll put some scale on this side. Look at the x-axis. I just wrote a couple numbers for the scale, but everyone in the world knows that one box is one step now. So what happened to this parabola when I changed x squared into x minus 3 squared? I moved the parabola 3 steps right. Think about that. Don't say, oh, let's subtract 3, let's go left. No, subtracting 3 actually moved it 3 steps right because it moved the vertex to 3 and 0. And let me go. We're actually doing good. Now, I want you to be really careful how you're thinking about what we're doing right now. First, you say, oh my gosh, slow, 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 parabola. These are just simple parabolas. How am I going to get to the good one? Okay, be very careful, because if I show you how to read a parabola like this, then the fancy ones just require one more step of reading. So pay attention to the basic building blocks here. And I want to go over to Desmos for a second, because I want to show you that pattern a little bit faster. So let's draw just some mellow parabolas right here, like y equals x squared. And then y equals 2x squared. And that looks like the drawing that I have here on the paper. Taller, thinner parabola. That's right. What about minus 1/2 x squared? Okay. In a sense, now that's a parabola, right? But it's a little bit wider or a little bit squashed compared to the red one. Let me squash that red parabola by multiplying by 1/2. Yes, now the red and blue are exactly the same proportion or shape, just the blue one is upside down because of that minus sign. Okay, let's play with this. Here's x squared, here's x minus 3 squared. You see how it's exactly 3 units to the right? That means if I wrote y equals x plus 2 squared, you could predict what happens. Notice I turned it off before it drew itself. But if subtracting 3 moves me 3 steps to the right, you'd be willing to bet all the money in your wallet right now that adding 2 moves me 2 steps to the left. Now think about this for a second. You got red parabola with its famous points, and then you got blue parabola and green parabola. They're all using the same points. It's just that I'm shifting the points to the right or to the left. So if I learn one set of parabola points, like -3, 9, -2, 4, minus 1, 1. And this might be the last time I list these points for you. Not because I won't, not because I refuse to list them, but I'm just saying after you see these points several times, they get burned into your mind. 2, 4 and 3, 9. You see that these points will be all the same on the next parabola, except they'll be moved 3 steps over. I'll add 3 to every x value. That's not what I wanted to do. Let me take all these points. This might seem like a long errand, but be patient. Let me take all those points and add 3 to every x value. That's a 0. That's a 1. That's a 2. That's a 3. That's a 4. That's a 5. That's a 6. You see, I just reproduced the same points, but now they're on the blue parabola. Let me take all those points again, but this time I'm going to subtract 2 from every x value, and that'll put the points on the green parabola. Minus 5, minus 4. You see them happening in front of you. Minus 3, minus 2, minus 1, 0, and 1. Now each point, each parabola has its vertex, right? And the vertex is just moved 3 units to the right or 2 units to the left, and all the other points are moved with it. Okay, good. Now let's try one more trick. What happens if I subtract 3? I move 3 steps to the right. What happens if I add 2 on the outside? What did I do to the blue parabola? I moved it 2 steps up. Let's change the color here, just so I can have different color on the screen. Here's 3 parabolas. Y equals x squared. Then y equals x minus 3 squared, which is 3 steps to the right. And now y equals x minus 3 squared plus 2. What does the plus 2 do? The plus 2 just takes every one of those dots and raises them by 2. And if I raise every one of those dots by 2, 3, 0 now becomes 3, 2. And 4, 1 becomes 4, 3. And so on. All the same dots, the 1, 3, 5 pattern, but just raised by 2 steps. What happens if I take this parabola and say instead of plus 2, let's say drop 5? Now I create a green parabola that's been dropped 5 steps down. Instead of vertex at 3 and 0, now the vertex is at 3 and minus 5. Let me hide the original parabola for a second. So do you see what adding a number on the outside does? This is kind of natural. When you say plus 2, you think it's going to go up 2, so it does. Let me change that color to red. When you say minus 5, you think it's going to go down 5, so it does. When you add or subtract a number on the outside, it moves the parabola up or down. That's called vertical translation. You just vertically dragged that parabola up or down by that amount. But notice when you add or subtract a number in front of the x or to the x, that kind of does the opposite of what you expect. Subtracting 3 moves the parabola to the right. That's a horizontal translation. Adding 2 moves the parabola to the left. Now let's do a quick multiplication of this green parabola in front of you. You know, what does this parabola say? Oh, the vertex is at -2 and -5. Do you see by reading this parabola, you automatically see the vertex at -2 and -5? But what happens if I multiply this out? Well, then this would be kind of lost. Let's FOIL that out. X squared plus 4x plus 4 minus 5 is -1. Now you see a green parabola and purple parabola, and they're right on top of each other. They are the same parabola. But this, let me emphasize this with a note. This form is called the vertex form because it displays the vertex -2, -5. And this parabola in this form is called standard form. Because this is displaying straight up, A is 1, B is 4, C is -1. Now, the moment that you realize that these two different looking equations gave you the same graph, you have a way to visualize where the vertex is. Do you see this vertex is at -2? How could I get this -2 from the 4? I will take -1/2 times B. -1/2 times B will give me the vertex. -1/2 times 4 is -2. That's exactly the center of this thing. And the -1 here hence stands for something, doesn't it? The -1 stands for the place where this green parabola strikes the y-axis. That's the y-intercept right there at -1. Notice that if I have this point at 0 and -1, on the opposite side, 2 steps to the right, I'm at 1. So 2 steps to the left, I'm also at 1. That's -4 and -1. The symmetry is just throwing points at me almost faster than I can graph them. Okay, we're about to take a break. I want to point out one more thing. Where does this parabola cross the x-axis? Well, that must be at the moment where x squared plus 4x minus 1 is equal to 0. But since x squared plus 4x minus 1 is the same as x plus 2 squared minus 5, I could, let me go back to the paper before we take a break, take x squared plus 4x minus 1 equal to 0 and solve it by solving x plus 2 squared minus 5 equals 0. How would I solve that? Square root method. X plus 2 squared is equal to 5. Square root both sides. X plus 2 is plus or minus root 5. So x is -2 plus root 5. Or x is -2 minus root 5. Now the square root of 5 is about 2.236. So -2 plus that would be -0.236. And -2 minus that would be -4.236. And do you see how quickly I see those numbers on the graph? There's 0.236 right there. And there's minus 4.236. What did you just learn? Solving the quadratic equation gives you 2 more points on the parabola. Okay, what we're going to do is bring this back and wrap it up into one giant parabola drawing program. But first, top of the hour, let's take a short break. So 12:57, let's, oh, sorry, I didn't share this image with you. So you could see the minus 4.236 and the 0.236. These are the x-intercepts. The y-intercept is that 0 and minus 1. You get all these points on the parabola for free. And you can fill in others with a symmetry. Okay, let's take a break here. 157, 102. Let's come back and pick this up at 103. And we'll draw some hardcore parabolas. I'm going to mute my microphone and stretch my legs for a few minutes. Okay, I'm just bringing it back here and wait for just a few seconds, just in case people are timing this by some watch. So I showed, or I was looking at my whiteboard there because I want to show you a particular calculation then, so that you can always locate the vertex. Because what you learn pretty quickly when you draw the parabolas is if you have the vertex, you have it all. You basically have it all. Because if you know the vertex, you know where to hunt for points. Once you got the vertex, just pick some points on either side and build the symmetry. And once you pick a point on one side, you can flop it the same distance over to the other side. So once you find the vertex, then you pick a couple points on the right or left. You can just flip them over to the other side. You've got your parabola drawn. So I want to show you how to instantly find the vertex of any parabola. And I have this written on the board, but let me write it neater on the paper and so you can see it being written. So you know that if I give you something like x minus 3 squared plus 4, then I'm telling you to move that parabola 3 steps right and 4 steps up. You say that's not 4 steps, that's 2 steps. Ah, I just chose my scale to be 4, 8, 12. Remember what I said? Remember what I said about you. You are the scale master. You choose the scale. Now, let's put a point here at 3, 4. And just pick points out on the left and right. 2. Well, 2 minus 3 is -1. -1 squared is 1. 1 plus 4 is 5. Now remember, this is 2, 4, 6, so 5 is right here. And then automatically there's a point on the other side at 4 and 5. Let's put in 1. 1 minus 3 is -2. Squared is 4. 4 plus 4 is 8. So I get an immediate point here at 5 and 8. Now, by the way, you notice here you went up 1/2. And then you notice here that you went up 3/2. So it's not going to be any up 1/2 of a box, up 3/2 of a box. Now it's not going to be any work at all to say next time I think I'm going to go up 5/2 of a box. Let's go up 5/2 of a box and see where we are. 5/2 is 2.5. That means I'm putting myself right here. Symmetrically over here. That looks like a good parabola shape. How high is that dot? That dot is at 6 and 12 plus 1/2, but each box is worth 2. That dot is at 6 and 13. Do I really get 13 if I plug in 6? Let's try it. 6 minus 3 is 3. 3 squared is 9. 9 plus 4 is 13. I've drawn a perfect parabola with a minimum amount of work. Plus 1 unit, plus 3 units, plus 5 units. Even using the scale of my boxes, plus 1/2 box, plus 3/2 box, plus 5/2 box. If you get a point out of place, you'll know it because your scale will look bad. Now, let's draw that parabola multiplied out. Y equals, what's x minus 3 squared? X squared minus 6x plus 9. What's plus 9 plus 4 plus 13? And I want to show you that even if I write the formula as minus 6x plus 13, I still know the vertex is at positive 3. All I have to do is use this formula for the vertex x coordinate is minus b over 2a. Now here a is 1 and b is minus 6. So what's minus negative 6 over 2 times 1? That's 6 over 2, which is 3. I can read the vertex here as quickly as I can read the vertex here. Now, what's the 13 do? 13 is really the y-intercept, right? So I can automatically pick a point on my vertex by checking the y-intercept. But how do I find the low point on this parabola? The x coordinate of the vertex is minus b over 2a. This is the full vertex. The y coordinate of the vertex is c minus b squared over 4a. And he also presents this in the book. And minus b over 2a is not too hard to remember. Maybe c minus b squared over 4a is a little bit more work to remember, but it's worth it. Let's try it right here. C is 13, right? So this parabola has a vertex at 3. That's a minus 6 over 2 times 1. I've already done that. But let's find out the y-coordinate of the vertex, which is c 13 minus b squared. B squared is positive 36 divided by 4 times a, and 4 times a is 4. So where is the vertex? 13 minus 36 over 4. 13 minus 9. 13 minus 9 is 4. So even if someone gives me a parabola like this, I can name the vertex if I remember this formula for the vertex. And that formula for the vertex is what I placed on this handout. And that's why I showed you that handout at the beginning. Parabola facts. The vertex you read in parabola in vertex form at H and K, but you read in standard form as minus b over 2a, c minus b squared over 4a. That always locates the vertex, and then you just start snapping off points left and right. Free points, sometimes, like the y-intercept of 0 and c. Okay, you got to see this in action before you really believe it works. So I'm using paper here that's kind of littering the paper is kind of bleeding through. That's not excellent. Let me grab another pad of paper that might not bleed through so much. But then I got darker lines, so there's no winning here, right? Let's draw this problem. How about minus 2x squared? Oh, plus 6x plus 3. I just made up numbers. But now I'll show you that even if you just make up numbers, you can draw a perfect parabola by using the patterns that we've discovered. You also, don't forget this, you could also type this into Desmos or your calculator and see the parabola. So let's say you draw this and you type it up in Desmos, doesn't come out like you drew. Well, you better find out why it doesn't look the same. But you always got a backup. Remember, your calculator is your backup. So here I got a is minus 2, b is 6, c is 3. So let's do the most important point first, the vertex. The vertex is at minus b over 2a and c minus b squared over 4a. Now in this problem, the b is minus 6, so I'll just carefully plug this in. Minus 6 over 2 times minus 2. Kind of using parentheses to make sure I don't lose any signs. And the c is 3. And the b squared minus b squared, which is 6 squared, over 4 times a. That's 4 times minus 2. Okay, so there's a little legwork here right now to work out these numbers. But believe me, once you have the vertex, it's worth it. So here's -6 over -4. We're going to simplify that. Here's 3 minus 36 over 8 negative. 3 minus 36 over -8. We're going to simplify that. 6 over 4, -6, -4 is 3 over 2. That's 1.5. This is going to be a vertex in between points, but we can deal with that. Why? Because we are scale masters. What's 36 over 8? Divide by 2. 18 over 4, divide by 2. 9 over 2. Notice it's a negative, so this is positive 9 over 2. 3 is 6 over 2. What's 6 over 2 plus 9 over 2? 15 over 2, which in plain English is 1.5, 7.5. Okay, now let's draw the parabola. That's all I need to draw the parabola, because I'll just pick out points left and right of this key point. I think the only thing I have to decide is my scale, really, right? So let's be generous with my scale. And I'll show you that if you just change one of the scales nicely, the other scale kind of falls into line. So I should go as high as 7.5 here. But I need to mark 1.5 on the x-axis. Do you know what I'll do to make that easier? Is I think I'll expand my x-axis. Let's make that 1 so that every box is worth 1/2. That'll make it very easy to mark 1.5. So you want to plan your scale. Now let's talk about the 7.5. Should I count 7.5 boxes up? Should I make every box worth 1/2 again? Well, that would require me to go to 15 boxes up. I don't think I'm going to do that. Let's just try straight 1, 2, 3, 4, 5, 6, 7, 8. Because marking 7.5, 1 1/2, 7 1/2 is not so bad. I just have to split the box between 7 and 8. So here's 3/2. Here's 7.5. And I have my vertex. No harm in labeling it. One and a half, 15/2. Now let's start to pick out some freebie points. What's the C tell you? If x is 0, the C, plug in 0, I get 3. C is 3. That tells me what happens when I'm at x equals 0. I get a free point right here at 0 and 3. But look at this, 3 boxes to the left, I'm at height 3. Symmetry demands that 3 boxes to the right, I'm at height 3. Starting to fill in my parabola. Do you want to plug in 3 in here and check that you actually get 3? Well, you certainly can, but you don't need to if you've got your points symmetrically placed. Put in a 3 here. 9 minus 2 times 9 minus 18, but 6 times 3 is plus 18. Minus 18 plus 18 plus 3 is plus 3. What would be another excellent point to mark? It's always, well, it's usually not too bad to plug in a 1. Ones are easy to insert. Let's insert a 1. Minus 2 times 1 plus 6 plus 3. 6 plus 3 is 9. Minus 2 times 1 is minus 2. So what's happened when I plug in a 1? I get minus 2 plus 9, which is 7. But the moment I get that point on the left, I take a box to the right and draw 7 also. Parabolas are always 2 for 1. You get 2 points for every point you calculate, except the vertex. The vertex is unique. The vertex is by itself. Do you want to try another point? Let's try 4. Let's try minus 1. Either one would be one step to the right or left. So let's try 4. 16 minus 32. So this will be minus 32 if I put a 4 in there. Plus 24, now I'm at minus 8. Negative 32 plus 24 is minus 8. Plus 3 is at minus 5. So let's mark minus 5 and 4. 1, 2, 3, minus 4. 5, 6, 7, 8, minus 8. Here's 4 and minus 5. And look at how it flows with the other dots. It looks like it's flowing in the parabola shape. But the moment I mark 4 and minus 5, I just have to take the same number of steps over on this side. Put a gentle line through the middle there if you like to count the boxes, but 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. At minus 1, I better get minus 5. You can try minus 1 and see the minus 5. Now this is pretty good parabola now. I think I could gently draw this, but I'm aching to know one more thing. Where does this cross the x-axis? By the drawing, it looks like it crosses around 3.5 and around minus half. Let me write down those estimates for the roots or the solutions to this quadratic formula. I'm guessing the solutions are 3.5 or minus 1/2. Now that's an approximate guess that I made from the graph. Let's do the quadratic formula. Quadratic formula, minus 2x squared plus 6x plus 3. I've already identified the a, b, and c. So now I say x equals my opposite of b, which is 6, plus or minus b squared, which is 6 squared, 36, minus 4 times a, which is minus 2, times c, which is 3. All divided by 2 times a, which is minus 2. Let's work this out. Negative 6 plus or minus. What do we got? 36. What do I got here? 4 times 2 times 3 is 8 times 3, 24. 36 and 24. Am I adding or subtracting? The 2 minus signs say I am adding. So now this is 60 under here, divided by minus 4. Let me slide this up. X is minus 6 plus or minus the square root of 60. The square root of 60 has got a perfect square. It's got a what? 4 times 15. So this would be 2 root 15 over minus 4. And if I canceled out, I gotta cancel out 2 correctly, but negative 6 divided by minus 4 is 3/2. Oh, there's the center of the parabola, 3/2. And plus or minus 2 over minus 4 will give me a minus or plus root 15 over 2. Well, let's try those two numbers. 3 minus root 15 over 2 and 3 plus root 15 over 2. Let's try them in my calculator. Reach back on the shelf, pull out the calculator. Get it out of the sun, so to speak, or out of the light. So 3 minus square root of 15 divided by 2 minus 436. It's not exactly minus 0.5, like I guessed up here, but it's darn close to minus 0.5. Now let's do the same thing again, but put a plus sign in here. Oh, excuse me, gotta get someone else in the room. Get some drop and come back. Let's put a plus sign in there. I got 3.436. 3.436. What did I predict from my drawing? 3.5. That's pretty good. Now, can I mark my axes to the nearest thousandth? No, that's not likely. But I can put this dot just shy of 0.5 negative. You know, darn close to 0.5. I can put this dot just shy of 3.5. Darn close to 3.5. And these are solutions to that quadratic equation. 3 plus root 15 over 2 and 3 minus root 15 over 2. Here's a message I'm trying to give you about parabolas. You can have as many points on a parabola as you like, and they're just coming out of the woodwork. And now you just gently, smoothly collect the points. You go from one point to the other, gently and smoothly, and you naturally create this parabola shape. And I do want your parabolas to be beautiful, smooth, rounded at the top to a nice hilltop or valley. Nicely labeled scales. Maybe I labeled more points than I needed to on the x-axis, but I wanted to see that 1.5 clearly. Here I just had the right amount of labels on the y-axis. Label your x-axis, label your y-axis, because you could use different letters if you wanted to. But label the axis with the letters you're using. And, you know, you can name these points as people tell you to name them. But check that out. I actually got 1, 2, 3, 4, 5, 6, 7, 8, 9 points on this parabola with really very little calculation. Maybe the quadratic formula was the most intense calculation I did here. Let me do another one. So what's the message? You got a parabola, get me the vertex. Get me the vertex. And then everything else will be relatively straightforward. Let me draw a parabola not in standard form. Oh, sorry, I jostled the table. Now this is called standard form, where you just give a straight ahead, ax squared plus bx plus c. And it's got its own beauty because you know the formula for the vertex minus b over 2a, and c minus b squared over 4a. But you also know the y-intercept. The y-intercept is a freebie, 0 and c. Because if you put 0 in for x, you clearly get c and only c out for y. So standard form is cool, but let's practice vertex form. And let me show you where that comes from. Vertex form is also excellent because it displays the vertex at H and K, and it displays the vertical scaling of A. And once I have that, I can multiply this out to plug points in, or I could plug points in directly. So you think about this for a second. If someone gives you a parabola, maybe you want both of these on your paper. Let's try one. And then let's try one with a kind of an extreme scale. So how about y equals 3x squared plus 12x minus 4. Now I'm picking numbers, that look kind of suggestive, but these are not going to be super kind numbers. But this is standard form. And I know how to find the vertex. What I also want to do is complete the square to show you what it looks like in this form. But before I do that, let's do the vertex. Minus b over 2a, that's minus 12 over 6. What's minus 12 over 6? Minus 2. I don't want to condone doing things only in your head. You should check that out. But if you do minus b over 2a, you get minus 12 over 2 times 3. Minus 12 over 6 is minus 2. How about the y-coordinate? You get negative 4 is c, and then you get minus b squared over 4a. Well, that's yuck. B squared is 12 squared, 144. How about 4 times a is 12? 144 divided by 12 is 12. So negative 4 minus 12. Well, that's pretty deep, isn't it? Minus 16. Now think about this for a second. That's what I think the vertex is. Who's to say that I didn't make a mistake? So let's put this in vertex form by completing the square. And remember, you've practiced completing the square. So let's do this. How do I complete the square? The number in front of the x squared has to be 1. But instead of dividing everybody by 3, that would change this parabola. Let's just factor that 3 out. And that leaves inside here x squared plus 4x. Now be careful. How do you create a number that you multiply by 3 to get negative 4? You can't like factor a 3 out of 4 negative, but you can say 3 times negative 4/3 is negative 4. So you're kind of like dividing by 3 in each piece, but not throwing away the 3. Okay, let's complete the square inside this square bracket. Move the minus 4/3 over, so I got some space. Give myself some more space. Do you remember the complete the square game? You take half the number in front of the x and square it. That gives you a +4, +2, +4. Then you add that to both sides. But I don't have a both sides here. Everything's inside this square green bracket. So what I got to do to make this legal, I added 4 to make it legal. This time I'll subtract 4. What does that mean? These red numbers have not changed the green thing at all. I just rearranged them. Why did I rearrange them? So I can see the perfect square. What is the perfect square? Remember how to find that? You just drop this 2 down, +2 that is, and that's your perfect square. X plus 2 squared is x squared plus 4x plus 4. Now you got to finish over here. -4/3 and -4 is -12/3. So what's -4/3 minus 12/3? -16/3. Now that you're done manipulating this, sorry, I erased my paper. It takes me a few steps to complete the square. Let's multiply by 3. 3 times x plus 2 squared minus, what's 3 times -16/3? -16. Do you see the vertex? -2, -16. Now I'm confident. Now I'm confident that I did this right. Now, one more step. I'm going to draw it, but I don't have a lot of paper left here, right? So what's the trick I showed you? When the A is 3, why don't you make every vertical box worth 3 steps, worth 3 units? And that will condense our graph. Okay, let's try it. Now, you notice I got to dip way down here. I got to dip down to 16. But if every box is worth 3, what is 16? 5 boxes? 5 1/3 boxes, almost 6 boxes. Okay, so in order to dip all the way down, and is this parabola opening downwards or upwards? Well, notice the 3. In either case, the 3 says this parabola is opening upwards. So let's draw a parabola that could go 5 boxes below the axis, and at a scale of each box is worth 3. So let's call this 1, 2, 3, 4, 5. Plan ahead. Good. So every box is worth 3. So let's call this 3, 6, 9, 12. No, I'm not going to mark -3, -6, -9, -12. Let's just do a -6, -12, -18. And on the top, let's just do a 6, 12, 18, 21. That's going to give me plenty of space. Remember, I am the scale master. What movie am I referring to? Famous movie? Who is the key master? It's neither here nor there, but if you like funny movies, it's old, it's not too old, but it was in color, so don't guess any black and white movies. Who is the key master and in what movie? I'll give you a second. You can probably Google it too. Okay, now let's draw the vertex at -2 and -16. So I could pop 2 steps over, or I could pop 2 steps and 2 steps over. I don't want to get arrogant, but remember, I'm the scale master. So why don't I make 2 boxes worth 1 step. I can do that. I'd be kind of curious what this makes my parabola look like. I want actor and movie. So my vertex at -2 and 16. Now notice this box right here is -15. So I'm going to have to eyeball this. From -15 to -18 is 3 boxes. So I want to go down 1/3 of a box from -15 to make -16. No one's going to recognize that I went down 1/3 of a box. So I'm going to tell them. There's never any harm in you labeling a point on a graph. It only makes you stronger. It only makes your graph better. Now let's try, what's my freebie point? Freebie point was at what? -4, that's the y-intercept. Okay, where's -4? Here's a -3. Again, -4 will be 1/3 down. I'll label it. But that's also 4 boxes over. And I'll go 4 boxes over to this side at the same height. 1, 2, 3, 4 boxes over. So now I got this. Maybe I should be, I don't know, now it doesn't help to have different colors here. But I'll be putting these points in red now. Okay, I need some in-between points here. But I love 1. 1 is the easiest number to plug in the universe after 0. So let's plug 1 into here. 1 plus 2 is 3. 3 squared is 9. 3 times 9 is 27. 27 minus 16 is 11. So give me 1 and 11, which is 1/3 below 12. And then I'll mark the same 11, 1 unit over on that side. Okay, a little bit better. Let's try -1. -1 plus 2, just mind your signs, is 1. 1 squared is 1. 3 times 1 is 1. Times 3 is 3. 3 minus 16 is -13. That would be 1/3 of a box below -12. But also on this side. Now this parabola is coming together. And you notice from 1/3 below -15 to 1/3 below -12, I went up 1 box. Then I went up 1, 2, 3 boxes. Now notice I went up 1, 2, 3, 4, 5 boxes. I think the next point is going to be up. 1, 2, 3, 4, 5, 6, 7 boxes. Well, I've almost run out of room there, but I'll fill it in and symmetrically on this side. Now I've got real parabola conformation. You know, these points are strongly suggesting a parabola. I might be able to draw a parabola here with my left hand. The only thing I might be missing is a crossing place. Do you want to guess what the crossing place is? Well, between these 2 points, let's just draw parabola. Gently, smoothly, from one point to the other. Smooth, gentle curve. Then back out the door. What's this crossing place right here? It's definitely below 1/2. Is it 0.4? About? Well, we can calculate and find out. Is this -4.4? Well, we can calculate and find out. How do we calculate? We do the quadratic equation, or we use the square root method. When is 3 times x plus 2 squared minus 16 equals 0. I'm not going to enjoy the fractions. X plus 2 squared is 16 over 3. Now I'll take the square root of both sides. X plus 2 is plus or minus. 16 is a perfect square. That's nice. But 3 is not. That's unfortunate. But I do get two answers. Subtract 2. Negative 2 plus 4 over root 3. And negative 2 minus 4 over root 3. Let's pop those in the calculator. I bet you money that they're 0.4 and 4.4 negative, approximately. Let's try it out right here. Negative 2 plus 4 divided by square root of 3. Now notice right there, I am not trying to get common denominators. I am not trying to rationalize denominator. I'm just checking this value here. And my result is 0.309. Okay, I guessed 0.4. It was a little more than 0.3. It's not bad. That's still not bad. Okay, what about this one right here? Change that minus or plus 4 to a minus 4. Negative 4.3. And our eyeball said negative 4.4. Okay, so it's negative 4.3, 0.3 approximately. I could be, add more digits, right? But I can't claim to draw 0.309 on this scale. I could just point to it and say, oh, that's 0.309. Nobody can contradict me, yes or no. But I want you to step back and look at this parabola. This parabola is essentially perfect. Now I know a computer could draw better and a calculator could draw better. In fact, I'm going to draw it on the calculator and the computer. But there's no person, not you, not me, not the fanciest math person at MIT, who could draw a parabola better than this. Beautiful, symmetrical, well labeled, exact points with a minimum of calculation. This is what I want your parabolas to look like. Now let's draw it in calculator side by side. And I even want you to go farther. I want you to use the same scale that you used here, because the goal will be to make your calculator screen look exactly like this drawing you made. Then you'll feel very confident. Okay, what was the parabola? I could type in the vertex form, but I could also type in the original, just so I can do some safety check, right? When I type in the original, then I'll be checking if I really did all my work right. Sorry, 12x minus 4. Now let's check out the scale. What do I want for my scale window? I want x min to be maybe minus 6, maybe minus 7. Let's say minus 6.5 to 5. And what do I want from my scale? I could count by ones. Sure, I could count by halves too, but that might be a little bit cluttered. Let's count by ones. X scale 1. Y scale is a little bit different. Y scale is going to be down here, minus 18, minus 21. I'm counting by threes. So that's going to be big, minus 21. And how far did I go up here? 24, 27? Even to get this point? 28, 29, 30? Let's run up there to 30. Big range. So I'm going to make every mark worth 3 steps. So this doesn't look too cluttered. Now think about this before we press the button. I've filled in this window with exactly the scale that I drew. So now anything less than the drawing in front of me is not successful. In other words, since I took care to use all these numbers, I'll know immediately whether my work was correct, because I either get the parabola just looking like that or somewhere else, and I'm in trouble. Try the graph. There's the parabola, pretty much looking exactly like this one. You want to have some more fun? Look at the calculate button. First row, fourth button, second function, calculate. Let's calculate the 0. Let's calculate where this reaches that axis. Calculator says, where do you want me to look? I'll say, why don't you look between 0 and 1? Right bound 1. And the calculator says, okay, I'll look between 0 and 1, and drew little arrows there. But why don't you give me a good starting place? It doesn't really matter where I set the starting place. I could say 0.5 as a starting place. Remember, we know the answer is 0.309 and change. And the calculator confirms it. Okay, I forget that this calculator types tiny. So I want you to get the close up of that. 0.309 is where this crosses the x-axis. And the same way on the other side. If I said calculate, 0, 0, root, solution, and I'll check between -4 and -5. -4. No, I want, well, I got to say it in the other order, -5 to -4. Again, the calculator says, can you give me a hint? Why don't I just say -4? That's a terrible hint. But the calculator will still find the crossing place. -4309. Now that y value, remember scientific notation from early in the course, the y value is just the calculator saying, well, it's not exactly 0, but it's really, really, really close to 0. 1 divided by 10 to the 12th, 1 divided by 1,000,000 times 1,000,000. Very small number. You want to see a 0 there, maybe. I understand, but that's because the calculator just approximates everything. Okay, doesn't matter. I am proud of that parabola, calculator screen or paper. But your goal is to make beautiful pictures on the paper. So you go play with this. Let's try these techniques. See if you can draw me some beautiful, beautiful parabolas. And I think on the homework 10 that I've given you, that's just exactly what I asked you to do, is just draw me a couple of parabolas perfectly. Let me back out of here. What am I doing? What am I doing? Let's get out of there. Let's get out of there. I'm just pulling up homework 10 because I want you to see that that's what I asked you to do, is solve a quadratic equation, draw me a perfect parabola. Solve a quadratic equation, draw me a perfect parabola. And I didn't pick nice numbers, but I didn't pick huge monster numbers either. So there's going to be fractions in here. Get used to it. But just carefully follow the steps that we did. And you can draw these two parabolas beautifully. You will.
Hey, Professor, I have a question real quick.
Go ahead.
So for the bottom two, where there's the 1/2 x squared plus 2x minus 1, could we easily just times 2 and just make that, just get rid of the fraction altogether?
Good. In one of them you can, in one of them you can't. If I am solving, then to say x squared plus 4x minus 2 is as good as to say 1/2 x squared plus 2x minus 1. You will find the same roots. And we've showed you that the other day when I had my scaled parabola that crosses at the same place. But for the graphing, I want a parabola with a equals 1/2. So good thing. If you're solving this, you want to make your life easier, go ahead and double everybody. because double this parabola is sweet, and double 0 is 0. But if I ask you to graph this parabola, sorry, if I ask you to graph this parabola, you can't double it and give me the same parabola. Let's try it. 1/2 x squared plus 2x minus 1. Close, 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 close. Okay, this will be the last thing I do. I promise. So y equals 1/2 x squared plus 2x minus 1. That's the parabola I want you to draw. Of course, if you doubled everybody, you'd still get a parabola, just not that parabola. You see, I don't want this blue one, I want the red one. Now the blue one and the red one have the same answers. That's what you suggested. So when I'm solving the equation, I could double everybody to get rid of fractions. But when I'm graphing, well, then doubling everybody makes a different parabola. Okay, good question. Okay, you guys just, first of all, take a day or two off. Enjoy the holiday, relax a little bit. And then you get right back into this and draw me some perfect parabolas, okay? What are we gonna do here? Let me stop sharing. I'm gonna stop screen. You guys have a happy Thanksgiving and I'll see you next week, 1 week from today.